In our previous session, we had seen about equation of motion and static and dynamic performance. Let us start off with thrust required in this session. Consider an aeroplane in steady level flight at a given altitude and a given velocity. For flight at this velocity, the aeroplane's power plant must produce a net thrust which is equal to the drag. Thrust required for an aeroplane to fly at a given velocity in level unaccelerated flight is given as Tr is equals to W by CL by CD, which is equals to W by L by D. Note that the subscript R has been added to thrust to emphasize that it is a thrust required. The thrust required curve for a given aeroplane at a given altitude varies with velocity V infinity, hence which is given as CL is equals to W by half rho infinity V infinity square S, where S is the wing area, V infinity is the velocity, and rho infinity is the density of air. Thrust required varies inversely as L by D. Hence, minimum thrust required will be obtained when the aeroplane is flying at a velocity where L by D is maximum. The lift-to-drag ratio L by D is a measure of the aerodynamic efficiency of an aeroplane. It only makes sense that maximum aerodynamic efficiency should lead to minimum thrust required. Consequently, the lift-to-drag ratio is an important aerodynamic consideration in aeroplane design. L by D is a function of angle of attack, which is shown here. Hence, when an aeroplane is flying at the velocity for minimum thrust required, it is simultaneously flying at the angle of attack for maximum L by D. Different points on the thrust required curve corresponds to the different angle of attack, which is shown in this graph. As we move from right to left on the thrust required curve, the aeroplane angle of attack increases. At high velocities, that is point A, most of the required lift is obtained from high dynamic pressure Q infinity, hence coefficient of lift and angle of attack are small. Also under the same conditions, the drag, which is equals to Q infinity SCD, is relatively large because Q infinity is large. As we move to the left on the thrust required curve, the dynamic pressure Q infinity decreases, hence the coefficient of lift, and therefore the angle of attack must increase to support the given aeroplane weight. Because dynamic pressure Q infinity decreases, D and the thrust required initially decreases. At low velocity such as the point B, Q infinity is low and therefore the coefficient of lift is large. At these conditions, the coefficient of drag increases rapidly, more rapidly than the coefficient of pressure decreases, and the drag and hence thrust required increases. This is why starting at point A, thrust required first decreases as velocity decreases, then goes through a minimum and starts to increase as shown at point B. The total drag of the aeroplane is the sum of the zero lift drag and the drag due to lift. For all the next examples in this session, two types of aeroplanes will be considered. A light single-engine propeller-driven private aeroplane approximately modeled after the Cessna Skyline as shown here. For convenience, we will designate our hypothetical aeroplane as the CP1, having the following characteristics of a wingspan of 35.8 feet, wing area of 174 feet square, normal gross weight of 2,950 lb, fuel capacity of 65 gallons of aviation gasoline, power plant of one piston engine of 230 HP at sea level, specific fuel consumption of 0.45 lb per HPR, parasitic drag coefficient of 0.025, Oswald efficiency factor E is equal to 0.8, and the propeller efficiency is 0.8. Next is the jet-powered executive aircraft, approximately modeled after the Cessna Citation 3. For convenience, we will designate our hypothetical jet as the CJ1, having the following characteristics of wingspan is equals to 53.3 feet, wing area is equals to 318 feet square, normal gross weight is equals to 19,815 lb, fuel capacity of 1,119 gallons of kerosene, power plant 2 turbofan engines of 3650 lb thrust. Thrust specific fuel consumption is equals to 0.6 lb of fuel by lb thrust R. Parasitic drag coefficient is equals to 0.02 and Oswald efficiency factor E is equals to 0.81. Now to find the thrust required, we have to assume the V infinity and then calculate the lift coefficient of lift, which is equals to weight by half rho infinity V infinity square S, where we know the density of air is equals to 1.225 and V infinity square we have to assume it, and S is the wing area. After calculating the coefficient of lift, we have to calculate the aspect ratio, that is equals to wingspan square by the wing area. After that, we have to calculate the coefficient of drag, which is equals to CD naught plus CL square by pi EAR, where we know the E is the Oswald efficiency. Aspect ratio is also calculated, and CL square is also calculated, and CD naught is the parasitic drag, which is already given in the characteristics. Then we have to find the CL by CD, which is equals to L by D is equals to CL by CD by substituting the coefficient of lift by coefficient of drag. Then we have to substitute the coefficient of lift, coefficient of drag and the weight in the thrust required equation, which gives us the CP1 values as shown here and CJ1 values as shown here. The graph for both the equations come like CP1, thrust required TR for a given aeroplane at the given altitude varies with V infinity, that is the velocity, and the thrust required curve is a plot of this variation has a general shape as shown in the graph. The CJ1 graph is here. So considering a jet aeroplane which is flying at a level unaccelerated flight at a given altitude and with velocity v1, the point 1 on the thrust required curve gives the value of the thrust required for the aeroplane to fly at a velocity v1. The pilot has to adjust the throttle such that the jet engine provides thrust available just equal to the thrust required at the point TA is equals to TR. Since we have to talk about the thrust available also in this graph, we will be explaining you this in the thrust available session. I hope you would have understood thrust required. Let us move on to thrust available in the next session. Thank you.